Hey, welcome back, CPSC 121, and we're going to try to do this again, but with structs. So the previous one, we used ints, and we looked at pointers and references, and now what I've done is I've defined a struct foo, which has an int a and a char b. Now, let's remind ourselves a struct is just a concatenation, or it just shoves the two pieces together. So the first 32 bits of this variable would be an integer, and the last 8 bits would be the char. So if I declare a variable like this, say foo x, then the first 32 bits, or the first 4 bytes, will be an integer. We'll say 42. And then the last byte, or the last 8 bits, will be a character. And what we want to do is we want to print it out. So I'll say cout, and I'll just print out what foo is. Now, to get at a field inside of the struct, I use the dot notation to get at that field, because as a static variable, I can get at different field names just by knowing what they're called, so A and B, and saying x dot, because x is the variable, a dot, and then name of the field, and we'll find the first, it will find the field called A. In this case, it's an int. And I'm just printing them out nicely so that we can look at them on the screen. So for the character, I'll say x.b, and I'll close that off. Oops. Oh, but I also need to print out its address. So since I'm running out of space, I'll do that on another line. Here, I don't have to do different fields. I can just ask for the address of x. Let's compile that and see how that looks. I made a mistake. Forgot the double angle bracket right there. Let's try it again. Compiles. Let's run it. I can't spell located. But yeah, we got x. It has 42 and has the character x in it, and it's located at that address, E920. All right. What shall we do? Well, let's print out a blank line so it's easy to read. And then let's declare a pointer. Now, to declare a pointer to a foo struct is just like declaring a pointer to an integer. You just say the type star and then the pointer name. So here it's going to be foo star p, and it's going to be equal to the address of x being that variable that we just declared earlier on line 10. Now, here's where I can print out what's inside of it. So I've set star p, or foo star p, equal to the address of x. Oops. Now, can I do this? Can I say foo star p is, and just say p? Sure, why not? Because it is an address. It's just going to print out an address. It's going to look inside of p and say, oh, hey, this p has the value of the address of x inside of it. So it prints it out just fine. If I tried to do that earlier with the x above, it would have thrown out a whole bunch of stuff, and I'll show you that in a second. And like the integers, we expect to find p at a different address. Now, let's say we wanted to print out p. I might initially want to say something like, by dereferencing p points to, this would be like what we did with the int, right? We had a pointer to the int, we dereferenced the pointer, and we got the int back out. Now let me compile this and see what happens. Horrible. So I'm going to scroll up and find the first error, and my gosh, there are so many different errors. It really boils down to this one thing right there. On line 18, I tried to say this. So I go to line 18, I'm like, what's wrong with that? What's wrong with that is there is no operator double angle bracket function that knows how to handle a struct foo. So it doesn't know what operator, there's just no operator defined for it, so I can't do this. So I can't do this unless I define a function that does that. And I'm not going to define an operator right now, but you could define an operator which would make our life a little easier. Instead, I'm going to say this. I have to dereference the parts of P. I'm going to use the arrow operator. And how should I do it? I'll say P arrow A. Because here on this line, I was able to use the dot notation because it's a static variable. It's not a pointer. Here, I'm going to, since it's a pointer, I have to dereference P to get to A. And that's why I say P pointing to A. And that's how I printed it out. Make sense? So let's review this again. Foo x, if I want to get to each individual field inside of x, I can say x.a, x.b, because x is a statically allocated variable inside a main. It's not a pointer. Now, if I have a pointer, p, which points to x, if I want to get to the fields inside of what it points at, I have to use the arrow operator. The reason it has to do this is it has to dereference the pointer twice, because first it dereferences p. It gets to that location in memory. Then it must dereference that part to get to A. So that's why we use this arrow notation. It's just the way it works in C++. Yeah, it is kind of confusing, but you just have to learn it. As you learn it, it'll become clearer and it'll make more logical sense of why it is there and why it's different. So if I compile this, it works and it runs. So I've got x, which has 42 and x in it. It lives at 9920, and then I have p. Its value is 9920, and it's located at 9918. Now, if I dereference it, I can get to 42 and x because p is pointing to x. Now, earlier I said, let's see what would happen if I just tried to print out x by itself. So if I did this and tried to compile it, it also throws up a whole bunch of errors because it's the same problem as when I said star p. Right? Invalid operands to binary expression. It's essentially saying, hey, listen, I know there's an x that's declared. I know its type. It's of struct foo. And you want me to somehow figure out how to send it to cout. Fine. But I can't find an operator that's defined. That means I, the programmer, have to define it. And in lieu of defining it, I'm just printing out one field at a time. So you just can't say that. Not unless you define the operator. Okay, so I've got the pointer. We had a little bit of fun with that. Why don't we try it with a reference? So same notation as when we did the reference for an integer. Here the reference is for foo, so it's foo ampersand space r. R is the reference, and I'm binding x to r. And we're hoping that it works kind of like a pointer. But the nice thing about the reference, because it's an alias, because it's not quite a pointer, I can use the notation that I used over here. So I can actually just copy and paste this right there. But instead of x, I'm going to say r, and r right there. And I can then say it is located and get its address. And we can also say that it's got the same address as an x, because that's the interesting thing about references. Forgot a space there. never can fit things just perfectly on a line. Let's try that. Let's compile that. Run that. Okay, so we set foo r, reference r, to equal to x. We can print out r just fine. We get to see what's inside of x. We see that, amazingly, r and x have the same address in memory, which is weird. That's kind of a, it's like r is different than x, but yet they're both in the same place in memory. So how is that possible? Well, it's because it's a weird thing. It is an alias of something rather than a true thing. So let's say I make a new foo. I'll call it y, and I set it equal to some other numbers. I'll say 17 and the letter x. Oh, sorry, I'll z. Let's do that one. Nice big different letter. And why don't we do the same thing? So I'll just borrow this from up here, and I'll change the x's to y's. And I don't need this comment here. Compile and run, and we see, great, everything's working as we expected. We've got this new foo y, and we've got some values set inside of it, a 17 and the letter z. Why don't we say if we can have p point to it? So I'll say p ampersand y and have p take on the address of y. And let's try printing this stuff out. Here, I'll just steal this stuff up here. Let's set foo equal to the address of not x but y. And p is, okay, look at p, and we don't need this comment. We already know we can't do that. And if we dereference it, we can get all these data members, or these fields. So we compile, we run. Amazing. So we created a foo y. It lives at 7908. We set p equal to it. So p inside of it has 7908, but p lives at 7918. Different places, right? Or different than x, or sorry, different than y. I can use the arrow operator and dereference it and get at the contents of y via p. So I print out 17 and z. Excellent. So now, why don't we see if we can do this with the reference. So I'll say r is equal to y. Now if r is equal to y, well, I'll just copy this and print this out. I'll change all the x's to y's. Blah, blah, blah. Has the same address of y. That's what we expect. And I run. Okay, so here's where y, it lives at E908. I have p, p works fine. P, if I dereference it, I get 17 and z, which is the same thing as y. I set r equal to y, and r is located at BE920. Wait a second. See, here's where it's funny. R has the address of BE920, or E920, and y has the address, oh, I accidentally put the address of x there. Let me fix this. Compile, run. Y has the address of 4908. R has the address of 4920. Who has the address of 4920? It's the same as x. R still has the same address as x. R is still bound to x. What we've effectively done is set x equal to y. So again, we didn't set r equal to x there. We actually set x is equal to y. And it has gone into the struct and magically assigned all the fields of that struct equal to the field of y. So if I print out what y is and what x is by copying and pasting the code that I have earlier, so I'm going to say foo x is this blah blah blah. So I'll do that right there, and I'll do the same thing for y. What we're going to find out is that y has never changed. X has changed because I had r bound to x, and I did the r is equal to y. y overwrote x. So now, even though they're at two different locations in memory, x has the same values as y because r was bound to x. And then I assigned y to r, and that means x got changed. The rule is you only can bind references once. You cannot rebind them. So once r was equal to x, it was equal to x forever. So you can't do it. Now, to expand upon the last video I did where I just bound it and showed you that it changes it, if I want to have another alias that has been used here, I need to declare it as a new alias. I need to say ampersand, not r, some other letter, m. Now if I'm using m and I do this, I change all these r's to m's, then what will happen is that it will be the same address as y. Oh, sorry, I meant to say foo. So here I've set m equal to y, and now m is an alias of y, and then when I do all that, x never changes. X stays 42, as you can see. Because of this whole thing with references, it makes the reference an alias to something else. Again, it's black magic. It's happening inside the compiler. It's a really cool thing because it allows you to move lots of data around in your program without actually having to copy it. And it provides a degree of safety because if somebody has a pointer, as you saw, we can get to the insides of things by using the arrow operator, and there's actually some other things you could do to get to arbitrary locations in memory, but references don't allow you to do that. They are like a opaque interface to some object, and they behave like pointers, but they aren't pointers. Yes, you're probably really confused by this, but that's why it's really important that you try writing some programs and experiment so it becomes clear why pointers and references are different. If you want more information, I strongly recommend reading the C++ specification or the Bjorn Sustrup book. Then you might find other things online that might help you understand it, but I really think writing programs and talking about it with your peers, and why not me, during office hours or whatnot, we can try to figure out why this works the way it does, and I can try to explain to you in different situations where it's useful.